Hi there, welcome to this lecture series on matrix algebra. This is lecture 11, part 2. We are studying the concept of a dimension of a vector space. And in the second half, we will take some examples and observe some properties, and then some examples of some ways of constructing a basis. Okay, let's get started. Now first, we will go through some examples of showing you that certain vector spaces have certain dimensions and give some reasons for that. Okay, so the first example is the following. And for the space of all 2 by 2 symmetric matrices, which is A transpose equals A, and the space V here will have dimension 3. So let's think about a 2 by 2 symmetric matrix. It will have 4 entries, 1, 2, 3, 4, and the additional property of being symmetric. Being symmetric means if you take the main diagonal, then the elements that are symmetric about this diagonal will be the same. So here this element will be the same as that element. So we can write a general 2 by 2 symmetric matrix as the following, and we can put 2 different symbols for the diagonal, let's say A and C. And those 2 off diagonal, they must be the same. So we can put just a symbol, a variable b here. Okay. So we see that we needed 3 coefficients here to represent this A matrix. And then we can do the following. And among these 3 coefficients, A, B, and C, we can construct 3 special matrices, that is making one of them to be 1 and the other 2 to be 0. Say, for example, I keep A to be 1 and put B and C to be 0. And this is this matrix here. We call it S1. And then you can have A and C to be 0 and put B to be 1. And that's this matrix here. We call it S2. And finally, we can keep C to be 1 and the other to be 0. And that's this matrix. And we call it S3. And then once we have singled out these 3 matrices, we see that any 2 by 2 symmetric matrix with this form can be written as a unique linear combination of S1, S2, and S3 in the following way. That is, AS1 plus BS2 plus CS3 will equal to the A matrix. Furthermore, one can also show that the 3 matrices S1, S2, S3 are linearly independent. Therefore, we can conclude now the set of these 3 matrices is a basis for the vector space V of all 2 by 2 symmetric matrices. Okay, let's take another example. Let's consider space V of all 3 by 3 skew symmetric matrices. So what is a skew symmetric matrix? That is the transpose of the matrix equal negative of the matrix. And then we say that this one has dimension equals 3. Let's check. Now let's begin by thinking about a 3 by 3 skew symmetric matrix. What general form does it have? Well, we remember that with this property here, we know that all the diagonals must be 0, so you don't need to assign any coefficients, they're just 0. And then the elements off diagonal that are symmetric in their position must be the negative of each other. say, if this, we denote the coefficient as a, then this one here will be negative a. And then if this is b, then the symmetric position here will be negative b. And finally, if this is a c, and then this position must have negative c. So we see that we have now again 3 coefficients to represent a general form of this general 3 by 3 skew symmetric matrix. Now we can take a similar approach. Among the 3 coefficients A, B, and C, we can go through them and pick one to be 1 and the other 2 to be 0. Okay, so if we take A to be 1 and B and C to be 0, then we'll have negative 1 and 1, and then 0 everywhere else. And that's this matrix. And we call it M1. And then we can assign B to be 1 and the others 0. So I will have negative 1 and 1 and 0 everywhere else. And that's this matrix here. We call it M2. And the last one will be keeping C to be 1 and let others to be 0. So we'll have this one here, and that matrix we call it M3. And then we see that a general form like this and can be written as a unique linear combination of these 3 matrices, M1, M2, M3, in the way that is A times M1, which will get AA here, or negative AA here, and then plus B times M2, which will give us negative B and B here, and C times M3, which will have negative C and C here. And you see that if you add up these 3 matrices, you exactly get the matrix A. And also one can show that the matrices M1, M2, M3 are linearly independent. Okay, so and then therefore we can conclude that the set of these 3 matrices, they form a basis. Now let's take an example of a vector space for smooth functions. Let's consider a space we call P3. P stands for polynomial. 3 stands for the highest degree of them, which is 3. So this is the set of all polynomials of degree less than or equal to 3. Okay, this is a vector space of dimension 4. Now first we will write out the general form of a polynomial of degree less than equal 3. It will look like this. So let's call it Q of x. It will equal to the sum of all the terms of power of x less than equal to 3. So the highest one is x to the power 3, so x cubed, and then multiply by some coefficient a plus x squared times b plus x or times c plus this is x to the power 0, so it's constant, times d. Okay, so that one in Q here is a general form of any polynomial of degree less than equal 3. Okay, so we see that there are 4 parameters, and we can again do the same thing as we have done. Okay, so letting d to be 1, let a, b, c to be 0, we get this function. Let's call it p0. It's a polynomial. And then on the second one, we can set c to be 1 and the other 3 to be 0, which will be just x. We call it p1. And then the next one will be let b be 1 and the others be 0. And then we get x squared and we call p2. And the last one is let a to be 1 and the others to be 0. Then we have p3, which is x cubed. So we see that any polynomial of degree less than 3 is actually written as a times P3 plus B times P2 plus C times P1 plus D times P0. And furthermore, the set of these functions P0, P1, P2, P3, it's independent. And therefore, this set of 4 polynomials form a basis of the space P3. And now let's make some observations. The first one. Now, if I have V1, V2 to Vk, k of independent vectors in the space V. So all of these are in the space of V, and then this set of vector is linearly independent. Okay. Then we know we can always find additional vectors Vk plus 1 to Vn, so that we will have a set of n vectors more than n is more than k, that this set will form a basis of V. Second, now if I have a set of vectors V1, V2 to V capital N, so capital N of them, and if I look at the span of these vectors, and we see that it equals V, the vector space. So here we don't know if this vector, the set of these vectors, is a linearly independent one or not. Okay. If that is the case, and then we might have too many of them, there might be some linearly dependent elements in there, then we can always have some procedure to remove some of these vectors, and in the end to obtain a basis of V. Okay, so these are two remarks regarding the basis of a vector space. So these will lead to some properties regarding the dimension of a vector space. So let's say if the dimension of a vector space is n, then every set of n linearly independent vectors, let's call them V1, V2 to Vn, is a basis of V. So if you have a space V and you already know the dimension is n, and for some reason, by some computational algorithm, you manage to construct n linearly independent vectors in V, then they can serve as a basis. Now the last one. So if I know the dimension of V is n, and this n we know, and then we also know that I have a set of vector V1, V2, Vn, and the span of it is exactly the vector space V, then this set is a basis for V. So in other words, if you have a vector space and you know the dimension is n, and then you have a set of vectors, and then what does it mean, span of this equal V? Well, that means any element in this V can be written as a linear combination of these vectors in a unique way. So that actually would imply that this set of vectors, they are linearly independent, and therefore they serve as a basis of V. Now let's take some examples. The first example is expanding the set of independent vectors and to obtain a basis. So to be specific, we have the space V, which is R3, and then we are given two vectors V1, V2, like that. So we can verify they're linearly independent, but it's not a basis. And The reason is that even though they are linearly independent, the span of V1, V2 does not cover the entire space R3. We can take a closer look to see that. For example, if you just take any general linear combination, C1V1 plus C2V2, and you do this calculation, then you know that you will have this as the result. That is, you will have C1 plus C2 on the first element, 2C1 minus C2 in the second element, and the third one will always be 0. So this linear combination will give you a vector in R3 where the third element must be 0. So one can easily find a vector, let's say V3, that's 0, 0, 1, and that one can never obtained as a linear combination of V1, V2, but that one is in the space V, right? So they cannot, V1, V2 cannot be a basis. Now, knowing that V3 is not included in the span of V1, V2, then we immediately know the set V1, V2, V3 is independent, linearly independent. And therefore, we can collect these three together, and then the dimension of this is 3. So we have 3 vectors, and the space R3 has dimension 3, and therefore this becomes a basis for the space R3. Okay, so another example is in the opposite direction. That is, we are given too many vectors and we want to eliminate some to find the basis. Okay, so let's consider the space V is R2, and we have a set of vectors. 4 of them, V1, V2, V3, V4, takes this form. And then we know that this set generates the whole space R2. And however, this set of vectors, the 4 of them, it's not a basis because they're not linearly independent. They're actually linearly dependent. We can easily observe that, for example, V1 and V2, V2 is just V1 times 2. So 2 times V1 minus V2 is the 0 vector. And also, between V3 and V4, we see that if I multiply V3 by 5, then this is 15. Or I multiply V4 by 3, and this becomes 15. And then they cancel each other. Okay? So they're not linearly independent. And therefore they cannot be used as a basis of R2. Okay, but then realizing these two relations, then we see that we can remove one of them, one of each of these relations. Say, for example, I remove V2 here, and then I remove V4 here. So I only take V1 and V3, which is now here. And it's easy to verify that this is linearly independent. And then there are 2 vectors, and then the 2 matches the number of the dimension of R2, and therefore this is a basis. Okay, so we saw that we could just remove V2 and V4 and obtain a basis. And then we can also remove another one. Say we can remove V1 and we can remove V3. Then we'll have V2 and V4, and we can also show that this is linearly independent as well. Therefore, it's another basis. Well, but however, we need to be careful which 2 vectors we remove. It's not like you randomly just remove 2 of these vectors and the remaining 2 will be a basis, and that is false. For example, if I remove V1 and V2, then I will have the set V3, V4. This is not a basis. That is because V3, V4, they are linearly dependent, because I have 5 times V3 minus 3 times V4 equal 0. Okay, so you have to be careful which one you remove, and select the ones that will give you a linearly independent set of vectors. Okay, so that is all for today's lecture. So next time we will use the knowledge we have learned here about the dimensions, and then we will apply them to matrices, and we will use that to define the so-called rank of a matrix. Okay, so I hope you enjoyed today's lecture, and I'll see you next time.